Alright guys, here is your video key for the 2019 free response questions. This is being originally filmed during the whole coronavirus craziness, and so I am going to do number 5 on these for future students, but those of you who are part of the 2019-2020 school year, you can just skip over the video key when I do number 5 because that material will not be covered on your AP exam this year. Okay, so in this problem, I'm going to operate based on the assumption you've already worked on these and that you've read the problems and you're familiar with what the question's asking. So we have a rate of fish going in a lake, and then we have a rate of fish leaving a lake. Part A says how many fish enter the lake over the 5-hour period. Give your answer to the nearest whole number. So remember, to find the amount of change of something, you just do the integral over the time period, 0 to 5, of the rate of change of that thing. So we do the rate of change of the fish entering the lake, and that will tell us how many fish entered the lake over that time period. And you can actually write it like this on the AP exam, since they defined E of t up here and called it E of t. If they didn't give it a name, you could give it your own name and then just write E of t to save yourself a little bit of time. And then you can just use math 9, and you should have ended up with 153 fish, rounded down to the nearest whole number. Okay, average number of fish that leave the lake over the 5-hour period. So this is average value of a function. So we know the rate that the fish leave is L of t, so we do the integral from 0 to 5 of L of t dt, and that will tell us how many fish left, but we want the average number of fish that leave the lake per hour. So average number of fish that leave the lake per hour, so we're finding the average of the rate of that the fish are leaving. So we're doing the average value of a function, so that's where you divide by 1 over the interval length, which is 5 minus 0. And again, you can just use math 9 for that, and you should get 6.059 fish per hour. All right. When is the greatest number of fish in the lake? And so on this one, you can look at it graphically, and the greatest number of fish in the lake will occur when the rate that the fish are going in is greater than the rate of fish coming out, and then that changes. And so, because if the rate that they're going in is faster than the rate coming out, then your value of the fish is increasing. And if it switches to the rate that they're leaving is faster, then the rate decreases. So we're looking for that change from increase to decrease. And so if we just look at the two rates, E of t minus L of t, and we want to find when that equals 0, and where it changes from E of t being greater than L of t to less than. Then that's what we're looking for. Or you don't have to set it equal to 0. You could just graph the two functions separately, and then see where E of t and L of t, how they compare to each other. So I'm actually going to do it that way. Show you a little calculator trick here too. So this isn't exactly like your guys' calculators, but it's pretty close. So in y equals, I've already typed for y1 our function for E, and y2 our function for L. And then if we graph that, okay, so the green graph is our E function. So what we're looking at is starting at the x-axis or the y-axis, the green graph is greater than the blue graph all the way until this intersection point. Right, well, it's hard to do, but right there. Okay, and now you can find that intersection point on your calculator. On this one, I can just tap it, and it shows me it's at x equals 6.204, rounded to 3 decimal places. And that's the answer that we want, because that's where the green graph, let me change my zoom back to here. That is where my green graph is no longer above. Sorry, this is a new app that I'm using here, and That's where the green graph changes from above the blue graph to below. Ah, that didn't work at all. Let's just do this. There we go. All right, now we can see a good picture of it. All right, so we're looking for that intersection point right there. Okay, you could also subtract the two and find when it equals 0, and then when it changes from above the x-axis to below the x-axis, that's the same thing. All right, and then D says, is the rate of change in the number of the fish in the lake increasing or decreasing at t equals 5? So in this one, we know the rate of change is increasing if this thing right here is positive, and if that's negative, then it's decreasing, because that's the total rate. That accounts for the rate of fish entering and the rate of fish leaving. And so you could just find E prime of 5. Or sorry, that's, erase what I said there. We want to know when the rate of change is increasing or decreasing, so we look at the derivatives of these two things, not those things themselves. So you do E prime of 5 minus L prime of 5, and you should end up with approximately negative 10.723, and therefore the rate, since that's a negative number, the rate of change in the number of fish is decreasing at t equals 5. Okay, number 2. Oops, I have some work on there already. All right, number 2, we have a velocity function. Part A, excuse me, justify why there must be at least one time for which v prime, the acceleration, is equal to 0. So if they're giving us a function and they ask us about the derivative of that function equaling a certain value, that's going to be mean value theorem. And so with mean value theorem, remember what we show here is that the slope between 2 points is equal to whatever, and then we know that the slope at a point equals that. So if we want to show that v prime equals 0, we show that the slope of v equals 0 somewhere. So if we just do v sub p of 0.3 minus v sub p of 2.8 over 0.3 minus 2.8, you get 0. Because I chose those values because those y values are the same right there. So I know if I find the slope between those points, I get 0. And then, therefore, by the mean value theorem, there must be a time where on this interval right here, there must be a time on that interval such that this will equal 0. And you can just say because of mean value theorem. Remember, for mean value theorem to work, the function must be differentiable, but it does tell us that it's differentiable right there. Graphically, just a reminder of what mean value theorem is showing us graphically. If you have some function and you find the slope between those 2 points, or any 2 points on that graph actually, then somewhere between those 2 points there is a tangent line whose slope would be the same. So maybe it's like right here. It's not going to tell you where that occurs, it just tells you that it does in fact occur. Okay, so that's mean value theorem. Okay, using a trapezoidal sum. So remember, from a data table for trapezoids, the area of a trapezoid is 1/2 base 1 plus base 2 times our height. Our height is the distance on the x-axis, which is the difference between those two numbers. So it would be the height for our first trapezoid. That's the height for our second one, so 1.4. When you subtract those, this one would be 0.3. And then base 1 and base 2 are just this number and this number. So that's base 1, base 2 for the first one. And then let's color code these. The second one, oops. Let's make those orange. And then for our second one, this is base 1, and then this is base 2. Okay, so you just do that for 3 different trapezoids and add those all together. I'll let you just look at the handwritten key to see the work on that, just to save you guys a little bit of time while watching the video. Okay, now on part C, we want to find the time interval during which the velocity of particle Q is at least 60 meters per hour. So what we can do is we can graph this and graph the line y equals 60 and find those intersection points. So let me go back to my calculator here, say done, y equals, clear that. All right, we're going to go 60 for that one. And for this one, our function is 45 square root of t cosine of, make sure you're in radian mode, 0.063 t squared. Okay, we graph that. Let's go to our standard viewing window here. All right, and we want to know when that's above 60, so I'm going to, let's see, zoom out. Oops, what did I hit? I want zoom to standard, all right. Okay, so there's our two lines, so we can find that intersection point and that intersection point. So that's the time interval when our velocity of particle Q is above 60 from t equals 1 point, oops, that's not right. There we go. 1.866 up until 3.519. Now, notice how I rounded those numbers when I said them out loud, but we're going to use those numbers for a calculation when we do the integral, because now we are supposed to find the distance traveled of particle Q during that time interval. And so don't use rounded numbers to do this calculation because those are our bounds. So you can do the integral using not rounded numbers of from 1.8661815 up until 3.5191744 of our function v sub q of t. dt, don't forget to put that dt in there. Okay, and you should get 106.109 meters approximately. Part D, it gives us an initial position for particle Q, and using the result from part B, which the answer was 40.75 meters. Okay, so we know that that's the position of particle P, and we want to know when how far apart particle Q is after 2.8 seconds. So now we got to do the integral of particle Q. So remember to find position, its displacement, which is the integral of velocity. So we do the integral from 0 to 2.8 of v sub q of t dt, and then plus the initial position, but the initial position here is negative 90, so minus 90. So that's displacement plus initial position gives you position, and you end up with approximately 45.938, and then subtract that with your answer to B to know how far apart the two particles are, which ends up being 5.188 meters approximately. Okay, no more calculators now, so we can put those away. We'll go to number 3. Okay, on number 3 we have a graph of f, and then the graph only goes from -2 to 5, but then it asks us about an integral from -6 to -2. But since they gave us this integral value right here, we can split that up and do an integral from -6 to 5 of f of x. That's equal to an integral from -6 to -2 of f of x dx, plus the integral from -2 to 5 of f of x dx. And that's important because this is a given value. They told us that's 7. And this is something we can calculate from areas under this graph. Okay? So ahead of time, I figured out what all these areas are. So this is 1/2 right here, this little triangle. And then we have this little triangle right here is also 1/2, that little guy. And then this one was 1/4, 1/4. And then this big triangle right here had an area of 9/4. And then remember, for this quarter circle, you're finding an area between the curve and the x-axis. So the area we're actually finding is this. So you do a whole rectangle area. This is in a 3x3 rectangle, which had an area of 9. And then you subtract the quarter circle, which is 9 pi over 4. Like that. Okay? So now we know that this is equal to 7, this guy right here, that was given. So we have 7 equals the thing we're looking for. So we just treat this entire integral like it's a variable. And then plus we find the integral from -2 to 5. And that was... I don't have that answer right now. So from -2 to 5, we have to do this area plus this area, which will be 0. And then this area plus this area, which will be 2. And then plus 9 minus 9 pi over 4, the green area. So that's 11. 11 minus 9 pi over 4. Okay, and you can just subtract 11 and add 9 pi over 4, which will end up giving you 9 pi over 4 minus 4 for your integral. So again, you're treating this whole thing like it's a variable. Just get this thing by itself because that's what you're trying to find. All right. Move that out of the way. Actually, I'm just going to delete that because you can just rewind the video if you need to see it again. Okay, on B, we're evaluating an integral. The easiest way to do this, in my opinion, remember with integrals where you have addition on the inside, you can just split that into two different integrals. Also, this is a constant multiple, which we can take out of the integral. So it's 2 times the integral from 3 to 5 of f prime of x dx plus the integral from 3 to 5 of 4 dx. And that's nice because this is just a constant. So you can either do the antiderivative, which is 4x, and then plug in the upper bound and lower bound and subtract, or know that graphically that's going to form a rectangle, because if we have a graph of y equals 4 from 3 to 5, here's 3, here's 5, here's y equals 4, you just get this rectangle and do the area under the curve. That's a height of 4 with a base length of 2. So that integral equals 8. Okay, and then this integral right here, well, we're doing the integral of f prime, which is just going to be f. So it's 2 times f of x evaluated from 3 to 5. And then from this integral, remember that answer was 8. So we have plus 8. And that's going to be 2 times f of 5 minus f of 3 plus 8. F of 3 was given right here. And f of 5 we can get from the graph. Okay? So I'll let you guys just plug those numbers in, or you can refer to the key that's already available to you. And then finally, finding a limit here. Remember, limits are as easy as just plugging in what x is approaching when it is plug-inable. And in this case, it is. So all I have to do is plug in 1. So plugging 1 into the numerator gets me 10 minus 3 times f prime of 1. F prime of 1, we can get that value from our graph, because when x is 1, we're just looking at the slope of this line, because the slope of that line is the slope at 1, and the slope of that line is 2. So we know our f prime of 1 value is 2, over f of 1, which is a y value we can get from the graph, which happens to be 1. Again, you should never guess those points. You should find the equation of that line and actually know what that point is. And then remember, arctan means tangent inverse, so the angle whose tangent value is equal to 1 is something you should know to be pi over 4. So this just gives us 10 minus 6 over 1 minus pi over 4. which is just 4 over 1 minus pi over 4. And I believe the rubric allowed that answer to be written like that. 4 over 1 minus pi over 4. Okay, so you don't even have to simplify that answer. All right, on to number 4. So what we have here is we have related rates. So this is where like multiple things are changing at the same time. So we're given dH/dt here. And notice how there's not even a t in the problem, but we're finding the derivative with respect to time. And so if we find the derivative of something, we're going to have to multiply by that variable prime. Unless it's t, the derivative of t would be 1, but the derivative of h is h prime, or dH/dt. Now, something special to this problem also, though, no matter what level this water is, as it's being poured in, let's say it was up here, this radius value doesn't change. So we do have a constant radius in this problem. That makes the problem easier because when we do the derivative of r, we can plug a number in for it before we find the derivative, and we don't have to worry about having an r prime value. Okay? So A says find the rate of change of the volume of the water, which was given to us right here. But again, RR, the diameter is 2, so RR is 1. R equals 1. Yay. So we're finding the rate of change of the volume, so dV dt. So V is really just pi h. So dV dt is just pi times h prime, or dH dt. Okay, dH dt, though, is this thing. So this then equals pi times negative 1/10 radical h. And it says when the height is 4, so now we plug in 4, evaluate this at h equals 4, and you get, when you simplify that, you should end up with negative pi over 5, and then it's rate of change of volume, so it's feet cubed per second for our units. Make sure you're focusing on units and getting those correct. B, when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? So now it wants us to say if this thing is increasing or decreasing. To show if anything is increasing or decreasing, you find its derivative. So we're going to find the derivative of dH/dt, which is, if you remember this notation, so we're finding that, and that's going to be rewriting this as negative 1/10 h to the 1/2. So you do power rule, bring down your 1/2, times the negative 1/10 will be negative 1/20, h to the negative 1/2, but then times h prime, okay, because of chain rule. Remember, we're finding derivative with respect to time. So you do that, and then we can substitute this in for h prime. So this is negative 1/20 h to the negative 1/2 times negative 1/10 h to the 1/2. If we notice, these two things will actually cancel out because the h to the negative 1/2 is on the bottom and h to the 1/2 is on top. So those cancel out. But if you didn't notice that, you can, at this point, you can just plug in 3 for h, because that's the moment in question, and you end up with negative 1 over 200. Sorry, positive, it was two negatives. So 1 over 200, which is positive, and therefore the rate of change of the height of the water is increasing when h equals 3. All right, and then the height of the water is 5 feet at t equals 0. Use separation of variables to find an expression for h in terms of t. So, once again, using this guy, let's get rid of that. Using this thing right here, we're going to do separation of variables. Now notice how there's not actually even a t in the problem. That's okay. That just means when we find the antiderivative of a constant, it's just going to be the constant times that variable that we're finding the antiderivative with respect to. So what I mean is get this dt over here, get the square root of h over here. So you end up with dh over square root of h equals negative 1/10 dt. Okay, so we separated the variables. Now we can write this left side in a much nicer way, where it's h to the negative 1/2 dh equals negative 1/10 dt. Now you find the antiderivative of both sides. Okay, so power rule over here gives us 2h to the 1/2 equals negative 1/10. And this is what I was saying, we just have a constant here, so the antiderivative is just the constant times t, the variable of integration, and then plus our constant c. They gave us an initial condition of t equals 0, h is 5. So we can plug in 0 and 5. So here we get 2 radical 5 equals c. So our c value is just 2 radical 5 directly. Okay, plugging that into the green equation gives me 2h to the 1/2 equals negative 1/10 t plus 2 radical 5. And then from here we just do some algebra and get h by itself. So if I multiply both sides by 2, I get h equals negative 1/5 t plus, divide by 2. Oh. Negative 1/20 t plus radical 5. And that's actually h to the 1/2, so then I just square both sides to get my final answer. There you go. Okay, again, you 2019-2020 students can skip this question, but I'm still going to discuss it for future students. All right, so here we have let R be the region enclosed by these two graphs, the y-axis and the vertical line x equals 2. Find the area of R. So remember to do area between two curves. This is our h of x right here. This is our g of x. To find the area between two curves, you just do the integral of top function minus bottom function. So we're going to go integral from 0 to 2 of h of x minus g of x dx. Now what I would do if I were you, and I showed this on the key, multiply all that out and then simplify that, and then you can subtract this and you can combine like this negative 2 with a number you get from over here when you multiply that out, and then do the antiderivative from there. I think that might be easier for most of you. The rubric shows it a little bit differently. You can either look at my work or the rubric's work and see, but that's just top minus bottom. Okay, now this one, we've talked about how we do different cross sections where they tell us the cross section is like a square or a triangle or a semicircle or something like that. Here, they're just flat out telling us, hey, each cross section has this area. So to find the volume of a solid, when you know the cross section, you do the integral of cross section area. So we're going to do the integral from 0 to 2 of our cross section area, 1 over x plus 3. And then that's it. Times the thickness gives you volume. So it's cross section area times thickness to give you volume. Okay, and then this antiderivative is just natural log of absolute value of x plus 3, evaluated from 0 to 2, gives us natural log of 5 minus natural log of 3. You can leave your answer like that. That's what the rubric did, which I was kind of surprised. I wrote it like this using a property of logs. Okay? So they just flat out told you the area. So you didn't have to do anything there. You just use that function. And then part C, we're going to revolve this region about the line y equals 6. So let me get this down here. All right, so if we revolve this about the line y equals 6, which is like this line right here, what that will end up looking like, roughly, get out of there, is something like this. See if I can draw it well the first time. Oh, that's pretty good. And then we reflect the bottom part, which will go something like, it looks something like this. Oop, not steep enough probably. Something like that. Okay? And so when we revolve the region, we end up with a solid that looks something like this. And we do have some empty space, like right here. Okay? So we're going to use the washer method. One of our cross sections. So remember, we're going to do integral of cross-section area times thickness to get our volume. So one of our cross sections, let me draw one here. So that's one of our cross sections, or one of the cuts we would make, whose cross section looks like this. It's a washer because we have some empty space. So we need this cross section area, which is 2 circles. So that cross section area is pi, what we call big R squared, minus pi little r squared. Please don't confuse the big R there with the region R, as they're not related. Okay? And so our big radius, our big R, is going to go from the x-axis, or the axis of revolution, down to the curve that's farthest away. Okay, so that's our big R, and that is equal to 6 minus g of x. Our little radius goes from here to the closer curve. So little r is 6 minus h of x. Okay, and so that's our cross-section area then is pi big R squared. Color should we use pink? All right. So our cross-section area is pi big R squared, 6 minus g of x squared, minus pi little r squared, 6 minus h of x, quantity squared. And we do the integral of that from 0 to 2 of this whole thing, because that's our cross-section area, times thickness, dx. And remember, you could take these pi's out and write them in front of the integral if you really want to. Doesn't matter if you do or not. Okay, so that's pi big R squared minus pi little r squared. Alrighty, and finally, number 6. Okay, they tell us that there's a line tangent to both f and g at x equals, or sorry, g and h at x equals 2. And so g and h have a slope at 2 that is the same as the slope of this line. So when they ask what's h prime of 2, that's just the slope of h at 2, which has to be equal to this slope of the tangent line, so that is just simply 2/3. Okay. The next problem here, they give us a function a and tell us to find a prime. Make sure you clearly indicate what a prime is, because they ask you to find it. Really, anytime you need to find a derivative at all, you need to clearly show that you found it. Okay, but for our a prime, using product rule gives me 9x squared h of x plus 3x cubed h prime of x. And then we're supposed to evaluate this at x equals 2. So plugging in 2 will give me 36 times h of 2 plus 24 times h prime of 2, which we know to be 2/3 from part A. So I'm just going to put a 2/3 there. H of 2 we know is 4. So instead of this, I can just write 4. So I'm going to get rid of that. Put a 4 there. Okay. Do some arithmetic, and you should end up with 160 after you do all that. All right, on part C, it says the function h satisfies h of x equal to that for x not equal to 2. It is known that the limit of h of x can be evaluated using L'Hopital's rule. So since L'Hopital's rule works here, then that means for us, it's either going to be an indeterminate form of either 0 over 0 or infinity over infinity. Remember, there are other forms that do exist, but for our purposes in our course, we only do 0 over 0 or infinity over infinity. So if I plug 2 into this, into h of x, I get 0 on top over 1 minus, I need to get a 0 down here, which means f of 2, because it's going to be f of 2 cubed, So f of 2 has to equal 1, otherwise I wouldn't get 0 on the bottom. Or in other words, more algebraically, I need f of 2, I need 1 minus f of 2 cubed to equal 0. So then you can add this to the other side, cube root both sides. In any case, you end up with f of 2 equals 1. So you have f of 2 equals 1. Okay, since L'Hopital's rule works, then we know that we can evaluate the limit as x goes to 2 of the derivative of the top over the derivative of the bottom. So doing the second part to help us find f prime of 2. So we do the derivative of the top using L'Hopital's rule is 2x over 1 minus, and then you have to do power chain rule. So bring the 3 down, f of x squared times f prime of x. Okay? And we're trying to find this at 2. So plug in 2. So we evaluate x equals 2. Gets us 4 over f of 2 we know is 1. We just found that, so right here we can make that equal to 1. So you just get 1. Oh, sorry, that 1 doesn't belong in my derivative. That's gone when we did the derivative. Sorry about that. The negative does belong, however. Okay, so you get negative 3 times 1 times f prime of 2. F prime of 2 is what we're trying to find. But since these are both differentiable functions, then we know they're continuous. And since both of those values equal 4, then the limit as h goes to 2 must also equal 4. So if we set this equal to 4 and then solve from here for f, so you're just solving for f prime of 2. So you can do a little bit of algebra and get f prime of 2 is equal to negative 1/3. Okay? So again, that's because we know L'Hopital's rule works. We know that h of 2 is equal to 4. So that means the limit, and since it's continuous, the limit as x goes to 2 of h must also equal its y value. Remember, so what I'm using there is this definition of continuity, of being continuous at a point. To be continuous at a point means the limit must exist. Limit as x goes to c of f of x must equal f of c. Okay? So I knew that f of c, our f of c was 4 up here, so I knew the limit must equal 4 because I know it was a continuous function. We're going to use that same definition here on part D. Okay? This actually uses the sandwich theorem, or also called squeeze theorem, which is something we skipped in 2019-2020, and then I intended to go back and teach you guys, and then the whole coronavirus thing happened, and we didn't get to do it in class. So here is your instruction on what the sandwich theorem says. Basically, we'll use the functions they have here. They're telling us that g is always less than or equal to k is always less than or equal to h of x. So graphically, for one function to be less than another, let's color code these things. I'll go orange there and green here. Uh-oh. It did that underline thing. Can't do that. All right. So graphically, if something is always less than something else, then that just means it's below it on a graph. So if this is my g of x, like that, then my h of x, no matter where I draw it, always has to be above it. And then k of x is between those two things, so it always has to be between it. It's sandwiched between those two things. Okay? So what we know about, it wants to know if k is continuous at 2. So we're going to use this definition right here. But we need this for k, so I'm going to use the appropriate variables here. So we want to show that the limit of k of x is, as x goes to 2, is equal to k of 2. That's what we're trying to find. Okay, but we know that these two functions are both continuous and differentiable at 2, and that the y value there equals 4. So let's say this is x equals 2 right here, not drawn to scale, and I continue these graphs. Both the green and the orange one have to go to a y value of 4 because they're continuous and differentiable. So let's say that's a y value of 4 right there. Again, not drawn to scale. So here's my y value of 4. So if the blue one always has to be between those two things, then the blue one must also go to a y value of 4 right there. There's nowhere for it to go if it's always sandwiched between them. Okay? So we now know that the limit of k as x goes to 2 must be 4. And then also, because we know at 2 g of 2 is equal to 4, and h of 2 is equal to 4, and k is always between those two, then k of x must also equal 4. I'm going to show you the rubric here, because it may have been a little confusing to look at it. All right, so what they're saying right here is since these two functions are differentiable, it means they are continuous. This is what I said. And therefore, both of their limits are equal to their y values. And that's all that's saying right there. That's the definition of continuity, of being continuous. Okay? And then it says, all right, since k is always between g and h, then the limit of k must equal the limit of g and h. So those two limits have to be the same. So we've shown that the limit of k is 4. And then, since k is always between those two and they both equal 4, it's between them or equal to it. So if they both equal 4, then k of 2 must equal 4. So what we've shown this to be true. We found the limit of this to be 4, because it has to be because of sandwich theorem or squeeze theorem. And we showed k of 2 is also equal to 4. Therefore, that is the definition of k being continuous at x equals 2. So the answer is yes. And that concludes our video.